is the distributive property of union with the intersection going to be true? Well, what this is very much akin to is basically saying, well, 2 times x plus y all in a bracket is the same as saying 2x plus 2y, right? We distributed the 2 into the bracket. That's very similar to what we're doing here. We're distributing the A union into this bracket. We're saying A union B, which is what we have here, and then A union C, which is what we have here, and then we take this plus and we keep it from in our bracket. So that's where we get our intersection symbol from. So this is akin to what we're really asking. Is this going to be true for sets? Well, how can we check that this is going to be true for our sets? Well, first let's try and visualize the set on the left-hand side and see if it's going to look exactly the same as the set on the right-hand side. So let's draw those out real quick. So here we have our set A, our set B, and our set C. And what are we interested in? Well, we are going to be interested in the following area. We're going to be interested in B intersect with C. So it's got to be the area that intersects with B and C. So B and C intersect in this shaded in area. And then we want to look at all the sets in this area with unioned with all the sets in A. So we're going to look at everything in A. So we want to shade all of A in. So this is what we're going to look for to see if we find it on the right-hand side. So we're interested in the shaded in area. So let's draw out the right-hand side and we'll ask ourselves, are they going to be the same? Well, let's draw out the 3 sets. Okay, so I've drawn out our 3 sets similar to how we did here, A, B, and C. And let's just take the first bracket, A union B. Well, that's just going to be the area, that's going to be concerning all of the elements in A and all of the elements in B, which is going to be this orange shaded in area we have here, okay? Now we're going to forget about this intersection for a moment. Now we're going to look, so just to clearly visualize, I've drawn that out. Now we want to look at the other bracket, A union with C. So that's going to be similarly to A union B, where in this case, we're going to be interested in every element in A and C. So that's what this is going to be. So we're going to want to shade in, need a better marker maybe for our green. We're going to want to shade in everything in C and A. And what do we notice? Well, we're interested in the intersection between the orange and the green. In other words, we're curious about the part where there's both orange and green. And what is that going to be? Well, we notice that we can just erase the parts that don't have both colors. This part here does not have green, so we can just erase that very quickly. Okay, and then this part down here doesn't have orange, so we can erase that because we're not interested in that either. Okay, and what have we found? Well, the areas we're left with that have both orange and green is the exact same shaded area we found on the left-hand side. So it looks like that this is in fact going to be true. Let's just verify this with just one more example where maybe they don't all intersect. Okay, so now we're looking at a case where maybe not all of our sets share something. So none of these sets share anything with C. So let's draw what we have on the left-hand side. We want to take the union, or the intersection between B and C. Well, there's no intersection between B and C because they don't share anything, so we can leave that alone. And then we want to take that nothing and include on top of that everything in A. So that means we want to highlight everything in A, which is going to be everything in this circle here. Okay, so that's going to be our left-hand side. Is that going to be the same if we take the right-hand side? Well, let's give it a shot. First, we want to take A union B. Well, that's going to be the entire area between A and B. It's going to be everything here. That's our orange. Then we want to take A union C. So that's going to be everything in A and everything in C. So we're going to end up highlighting all of A and then all of C. And then because we're interested in the intersection between these two, we're interested in the areas that have both green and orange. So we can erase the parts that don't have one of the two colors or neither of them. So this side does not have green, so we can erase this side of our Venn diagram. And then this side doesn't have orange, so we can erase this side as well over here. And what do we find? That yes, it does look in fact identical to our set over there on the left. Now let's try one more orientation of this. Okay, so what if the parts that are in common are not going to be our union? What if the things we have in common are not going to be with our A? So our A doesn't share any elements with B or C, but B and C share some elements. So what is that going to look like? Well, we're interested in the area with B and C, the intersection between B and C. So we're going to be interested in this section right here down the middle. And then we're going to be interested in this section as well as everything in A. So we're going to want to be interested in everything in A. So are we going to get the same image on the right-hand side? Well, let's have a look. Let's first do our orange. Let's highlight everything in A and B. So that's going to be everything in A, everything in B. Okay? Then we want to highlight everything in A and C. So that's going to look something like this. It's going to be something like that and something like that. And then we want to ask ourselves, well, what parts have both colors? Well, we notice that this right-hand side doesn't have orange, so we can exclude that. And this left-hand side doesn't have green, so we can exclude that. So it's looking like it's true in this case as well. Let's just try one more example before we start writing down the proof. Okay, so what if none of the sets have any elements in common, so they don't have any intersections whatsoever? Well, let's ask ourselves, B intersects with C. Well, we can't shade anything because B and C don't share anything, so there's going to be nothing to intersect. Okay, but then we want to take that nothing and also include everything in A. So that means we're going to highlight all of A. So that's going to look like this. So we're going to want to look for something that looks exactly like this on the right-hand side. Let's see if we get that. So if we have something like A union B, we're going to want to include everything in A and everything in B. So we're going to highlight all of that in orange. Then we want to look at A union C, which means we're going to want to highlight everything in A and everything in C. So that's going to look something like this. And what do we find? For the intersection, we want to look for the areas that have both. And we notice B and C, B is missing green, C is missing orange. So we can erase these, which is going to, in fact, leave us with what we found on the left-hand side. So it's looking like this is definitely going to be true. So let's go ahead and prove this. So before we prove this, let's remind ourselves that because this is an equivalence, we have to show that everything on the left-hand side is going to be in the right-hand side, and everything on the right-hand side is going to be in the left-hand side. So what does that mean in math? It means the following. So this means that the left-hand side has to be a subset of the right-hand side, and the right-hand side has to be a subset of the left-hand side. Every element in this set must be in this set, and every element in this set must be in this set. So both of these have to be true in order for them to be equal to each other. So that's going to be the two cases we have to prove in our proof to show that this relationship is going to be true. So first, let's start by writing down our supposition in our proof. And what is that going to be in this case? Well, this is a hidden for all proof because we're looking at any set A, B, and C. These can be anything. We haven't restricted them to anything, which is why I did so many examples to verify that they work. So let's first start by saying let. And what are we going to let? We're going to let A, B, and C be sets. Fantastic. So now the reader knows what we mean when we refer to A, B, and C. Now let's start by checking our first case. Okay, so our first case is going to be to check that everything in here is going to be in here. So what does that mean? We're going to start by sketching our proof. How are we going to do this? Well, we want to get from A union B intersect C, and we want to get to A union B intersect with A union C. So this is our start. This is our goal we want to get to. And in order for this to be true, it must be that every element here has to be in here. So you want to say that for some element x, and this x is going to represent all of the elements in here, it must all be here. So all of x must be in here because x represents all of the elements in here. So what can we do? Well, first let's start by unpacking what it means for x to be an element of this. For x to be an element of this, it must be that x is an element of B and x is an element of C, because that's what the intersection means. And then looking at the union, it means that or x is an element of A. That's really what it means. X either has to be an element of A or x has to be in B and C. Those are the two options we really have here. So what do we want to look at next? So next we're going to look at what we want to prove. What is our goal? How do we get from here to here? Let's look at this. So we need to get A union B and we need to get A union C, and we have to get it so when we get these two statements, it is an or in between them. So let's first work to try and get A union B. How can we get that? Well, we're going to say that if X is in B, so we can say if X is in B, then X must be in A union B, right? That makes sense. And the same thing here. If X is in A, X is going to be in A union B. Fantastic. So we got that part down. Next, what can we say? Well, we can say when X is in A union B, we can also then say that X is similarly, maybe I'll make some more space here, maybe actually. Okay, so we got this. Maybe let's also try and get this now. We're going to say that when it's in A, it's also going to be in A union C. So we have that X can be in both of these and X can be in here. Okay, when X is in C, what does that mean? Well, it means X can definitely be in A union C. So what are we looking at? We're saying, okay, we got our two parts. We got our A union C and we got our A union B's. We got from B and A and we got from C and A a pair. So how can we get the intersection now? Oh man. I mean, I could say there's an and here and an and here, and then there's an or here, and then these are the same, so we can maybe like factor them out. We can factor this out, and then that leaves that together maybe. But I'm not sure if I'm allowed to say that. Let me do some more thinking. Okay, here's my thinking. We can then say if X, we're going to say these are separate. We're going to get rid of the and for a brief moment. We're going to say if X is in here, or if X is in here, then we lead to here. And then here we're going to say something similar. If X is in here or X is in here, then it leads to here. That's what I'm thinking. X can either, it's an or, right? Because we're looking at an and. No, it has to be in both. Ugh. Yeah, I think this makes sense. Because it's in B and C, it's going to be in this and this, which means it's going to definitely be in the intersection of the two because it's in both. It's in both, yes, okay, that makes sense. So because it's in both of these, right, imagine this was a set and this was a set, and because we have this and, we're saying that it exists like this with this little shaded in area in the middle, which means that we have to have this intersection sign, okay? And similarly here, we pretend like this is a set and this is a set, and we're having this be the case that it's for both. For it to be for both, it must be that both of these sets, we're going to picture A union C is a set and A union B is a set. And then for something to be in both, to have this and, it must be that you have this intersection here, which is where we get that from. Okay, I think I got this. Let's try and put this into words. So we start by creating our variable x. We say, suppose x is an element of A union B intersection C. Then let's break apart what this means. Then x is an element of A or x is an element of B intersect C. Okay, we take things slow. We don't want to immediately jump to here. This was just our sketch. Then we can break this apart, or actually no, let's just stick with this. We can then say if x is an element of A, then x is an element of A union B, and x is an element of A union C. So x is going to be an element of A union B intersect with A union C, since it must be in both. Okay, fantastic. Now we want to look at our B intersect with C. Then if x is an element of B intersect with C, then x is an element of B and x is an element of C. Let me just move this writing over. Okay. And then we can say, maybe, yeah, we'll just put a full stop. We'll say, thus, x will definitely be an element of A union B, and x will definitely be an element of A union C because it's in C and it's in B. So x is going to be an element of A union B intersect with A union C, as it must be in both. And then we can conclude that this is true, meaning A union B intersect C is a subset of A union B intersect with A union C. Okay, we've done our first case. Let's go ahead and give the second case a shot. So for our second case, we want to show that this is going to be a subset of this, which means all the elements in here must be in here. So what we want to show is, for some element, we'll say y, and this y is going to be any element in here. So it's going to kind of represent all of the elements here. That y is also going to be down here. So if y is in here and it represents all the elements, and y is in here, which means all the elements here are in here, makes this a subset of this. So let's think of how we're going to do this. We need to get from here to here. Let's unpack our definition for what it means for an element to be, for y to be an element of this. So this means that y must be an element of A union B, and y must be an element of A union C, right? We've broken those apart. And then we can say that these then break up each into saying y must be an element of A, or y must be an element of C. Similarly here, y must be an element of A, or, I didn't write that very symmetrically, y must be an element of A, or y must be an element of B. Okay, so more clearly we've gone from one expression to two, from 2 to 4, and now maybe we're hoping to bring this back. And there's going to be an and, of course, still being carried out through here. So let me just erase that for now. How do we get from here to here? Well, we need to get it so we have B and C. We have to get that condition. And then we have to get it that it's always going to be an A. So what can we say? Well, we can definitely say that in the A case, y is going to be an element of A union, or we can just immediately jump from here to here. So it's just figuring out these two. How do we get these two to get to here as well? So we need y. We need to basically get it so y is an element of B and C. That's what we need to get. Okay, so I think I figured out how we're going to connect these two to our goal. Notice that for this to be true, y has to be either an A or B, or A or C. So we're going to go down, for example, in this case, we've already gone down the path that y is going to be an A. So we've gone down this path already, right? But we haven't tried going down the other path. We haven't tried, I'll maybe make this orange, we have not tried going down the path that y might be in B. But what does it mean for y to be in B? It means that y is not going to be in A. So what does that mean? That means if you go down the path of y being in B, it means y was not in A. And if y wasn't in A, then it means it wasn't in A here, which means that it also must have been in C at the same time. So we're going to argue that y is either in A, or the other alternative is going to be that y is not in A, which means y must have been in B, and y must have been in C, because that is the only other path we have here. So let's go ahead and write down this proof. So first we're going to start by supposing our element y. We're going to say, suppose some element y, which again is going to represent all of the elements in this set here. Suppose y is going to be an element of A union B intersected with A union C. Fantastic. Then we want to unpack what this means. So we're going to say, then y is an element of A union B, and y is an element of A union C. Fantastic. Okay, so then we can say, since y is an element of A union B, then y is an element of A, or y is an element of B, right? And then we can say, if y is an element of A, then y is an element of A unioned with anything, or in this case, B intersection C. We're going to copy this sentence down with our A union C. We're going to say, next, y being an element of A union C means that y is an element of A, or y is an element of C. If y is an element of A, then y is an element of A union B intersection C. Fantastic. Now let's do I highlighted in orange. So notice in both of these scenarios, we're saying y is an element of A. But the alternative is going to be, well, what if y is not an element of A? Well, then that's going to make the following true, that y must be both in B and in C, because both of these must be true at the same time. So if they're not going to be in A, the only way y can be an element here is if it's in B. Only way y can be an element here is only if it's in C. And both of these must be true, so it must be both in B and C. So we're going to say, alternatively, if y is not an element of A, then y element of A union B means y is an element of B, and y union AUC means y is an element of C. We're going to make some more space here. Just got to put these down here for now. Okay. And we're going to say, since y must be in both, since y is an element of AUB and y is an element of A union C, and y is not an element of A, then y is an element of B and y is an element of C simultaneously, making y an element of B intersection C, so y then becomes an element of A unioned with B intersection C. There we go. And then we want to conclude our final statement that because we've shown that any element in here is going to be an element here, that means this is going to be a subset of this. So let's quickly finalize, just write a quick sentence explicitly stating that. Therefore, A union B intersecting with A union C is a subset of A union B intersect with C. Fantastic. Okay, so again, this worked because we are now looking at the case where it is not going to be y in A, and because it has to be in both of these sets and it's not in A, it must be that it must be in B and C simultaneously. Fantastic. And now we can just write our concluding statement. We've showed that they are subsets of each other, which means that they are equal to each other. So we can just write, let me quickly check if the camera even will see this bottom side of the whiteboard. Okay, we're good. We'll see the bottom side of this whiteboard if I were to write down here. So let's write given A, or no, we'll start with our first case. Given A union B intersect C is an element of A union B intersect A union C, and A union B intersect A union C is an element of A union B